Thank you, Doug, for those kind words, and thank you to the organisers of Minds and Wines for the invitation to present here today. It's a great pleasure to actually have the opportunity to see so many people in person for the first time in 2 years. So, to kick off the conference, I thought what maybe it would be useful for me to do is to give a little bit of an overview of mineral systems that form in convergent margin settings from outside of the Tasmanides. So take a little bit of a look at the mineral systems that are diagnostic of magmatic arcs in particular around the Pacific Rim, and just reflect a little bit on some of the lessons we get from those mineral systems that could impact on exploration here in the Tasmanides. And so we'll try to touch a little bit on discovery opportunities. Now, given my personal biases, I'm going to focus on the porphyry mineral system, and we'll explore in that briefly porphyry copper, epithermal gold, skarn and carbonate replacement deposits, so we won't be able to do a very deep dive here, and I apologise to VHMS and orogenic gold fans, I can't fit them in today. We'll look at some variations on a theme that have shown up in different environments, just to sort of highlight the variability in these systems and to reflect on whether we have potential for that sort of discovery in the Tasmanides. Porphyry copper system actually extends all the way from the mantle to the upper crust. It involves elements that are derived on oceanic plates that are generated at mid-ocean ridges, and we wind up with mineralisation commonly occurring in magmatic arcs in convergent margin settings. So these are, very large mineral systems involving components from large parts of the Earth's crust and mantle. There are key elements in the formation of a porphyry mineral system that lead to the generation of fertile magmas, okay? So we need magmas that are able to carry metals, sulphur and water from the domain of partial melting all the way up to the mid to upper crust where the ore deposits form. So they're specialised magmas, and first of all, they need to be oxidised. So we want metals and sulphur to behave incompatibly in a melt so they can be carried together from the zone of partial melting. So porphyry magmas are magnetite series intrusions. They're associated with oxidised magmas. They also need to be hydrous magmas. So we need to carry large volumes of aqueous fluid, and we need to be able to exsolve that in the upper crust. So that means a fertile magma will also contain minerals that are hydrous. And so commonly in intermediate magmas we get hornblende as the indicator of a fertile magmatic suite, and as we go to more evolved compositions we'll get biotite. So these are critical components for the magma to have the metal carrying capacity. Now, magmatism is common in convergent margin settings. We see widespread volcanism. What we actually want to do to form a porphyry deposit is to perturb that. We actually want to slow down and ultimately, if we can, stop volcanism and store magmas in a mid-crustal magma chamber. So I'll see if we get the laser pointer working because it'll be easier to do that. So these magmas are being derived from a zone of partial melting in a metasomatized mantle wedge, migrating up in dike swarms. We don't want them to continue to the surface. So we want some sort of tectonic perturbation to disrupt steady state subduction and allow a magma chamber to form as a batholith or a pluton in the mid to upper crust, maybe 10 to 6 kilometres depth. And in that environment, we can then cause fractional crystallisation and ultimately exsolution of large volumes of aqueous fluid, which together with melts erupt out of the magma chamber up fault intersections generally, forming stocks and pipes and dikes, and these are the focus for a porphyry mineral district, and they form the heart of your actual ore deposit cluster. So all those elements have to come together to form a porphyry mineral system. Now, if we get into a porphyry mineral district itself, there's opportunities for different styles of mineralisation to occur in a sea of hydrothermal alteration. So there's a lot of altered rocks, and there are small domains where we might get high-grade ore. Now, on this cartoon, I've sort of divided it to the left and the right, what I call the green rock and the white rock environments, because I'm trying to show you in oceanic island arcs, the common host rocks are volcanic rocks, and so we wind up with propylitically altered volcanic rocks distal to the intrusive centre. And as we have here in the Macquarie Arc, lots and lots of epidote chloride alteration. But if you're in a continental arc, in places like the US or in the Andes, you may wind up forming your porphyries in a sedimentary basin. Your host rocks might be carbonate platform rocks, you might get siliciclastic rocks. You get very different alteration depending on the protolith. So sort of trying to show that on this cartoon. We'll explore that in a little more detail as we go on. The centre of the district here, we have a multi-phase porphyry intrusive complex forming a mineralised envelope, which is shown here in stippled pattern. So the ore of a porphyry deposit is located both in and adjacent to the intrusive phase, and it's then surrounded by a pyrite halo, which is of variable dimensions. And so when we're exploring for these, we're looking geophysically for magnetite in the intrusions, we're looking for pyrite in the pyrite halo, we're looking for the geochemical anomalism that goes with all of these features. Above a porphyry, we get a really complicated domain of alteration that overprints the early alteration, and it's what I refer to as the transition zone. As we transition from the porphyry to the epithermal environment, we get white mica and then high temperature clays and silicic alteration that ultimately form this thing we call a lithocap. And so let's take a look at these in a little more detail and look at the mineralisation that occurs within them. The core of a porphyry deposit, if you're looking for one of these, there's a couple of things that really are the signature that you're in the middle of your deposit. First is the multi-phase intrusive complex, and second is normally we will see a well-developed vein stockwork in the heart of a strongly mineralised porphyry. This example, you're looking at a rock sample from the Christmas porphyry copper moly deposit in Arizona. The bottom part of the photo, you see a beautiful conjugate vein array, cross-cutting veins. These are quartz, K-feldspar, sulfide veins associated with biotite, magnetite, orthoclase alteration of a plagioclase hornblende ferric monzonite porphyry. Very strongly mineralised rock. It's an early mineral intrusion, and that's where the grade sits. There's also a late mineral intrusion that is cutting the veins and is cutting the early intrusion. This is a more crystal crowded feldspar porphyry with a very low vein density, much weaker alteration, and much lower grades. So this is normal in porphyries, to see these multiple intrusive phases. What you've got to hope for is you get a large amount of the mineralised intrusion, not too much of these low-grade to barren intrusions. So if you've got a porphyry prospect and it gets split apart by one of these big barren intrusions, it can really kill the economics of the deposit. But it's also worth remembering when you're drilling a porphyry system, you might be drilling the barren intrusions, and it just takes one drill hole across this boundary for you to hit the high-grade part of the system. So keep in mind this multi-phase intrusive complex as part of what you're dealing with. The intrusions themselves vary from province to province. Okay, so what's going on in a given geodynamic setting ultimately sets up certain magma compositions to being formed. Porphyry deposits form across a spectrum of intermediate to felsic intrusive compositions. Here we can see quartz diorite porphyry from the Philippines. This is producing high-grade copper-gold mineralisation. Tonalite porphyry from Indonesia. Here in New South Wales, our quartz monzonite porphyries at North Parkes and Cadia. All of those have produced copper and gold mineralisation. So it doesn't matter that the magma composition's a little varied. They're all magnetite series. They're all hornblende ferric. These ones on the right, they're associated with copper moly mineralisation. They're a bit more fractionated. So we've got dacite or granodiorite porphyry here at Chuquicamata. This is a true granite porphyry from Yerrington. They're all producing mineralisation. The thing that binds them together is their porphyritic texture. And so that two-stage crystallisation history that we see in these magmas is a product of the mineralising process. The phenocrysts are growing slowly and in the melt, and then what's happening is an aqueous fluid is exsolving, it is migrating to the top of the magma chamber, and eventually the fluid pressure exceeds the lithostatic load and the tensile strength of the rock mass. The fluids break out and form a vein array, or in exceptional cases a breccia complex, and the magma decompresses. And it's the decompression that causes the ground mass to crystallise. So this is a pressure quenching texture, not a cooling texture, and it's why we have a family of deposits called porphyries. That process is common to all porphyry deposits. At their heart, we find porphyritic igneous rocks. And typically, in the guts of a porphyry, you're going to see potassic alteration, and it will vary depending on protolith. If you're in mafic to intermediate rocks, this quartz magnetite biotite vein you see here with a bit of chalco, it has a biotite alteration halo. That hornblende phenocryst here is completely pseudomorphed by secondary biotite. So explorers need to be able to pick that shreddy biotite with their hand lens. They need to recognise this is softer than hornblende. The edge of the biotite is fuzzy. And here in the Macquarie Arc, that biotite gets retrogressed to chlorite, but it preserves this texture. So you're looking for shreddy chlorite after shreddy biotite after hornblende. And that's a sign that you're getting close to the mineralised centre. In the intrusion itself, we're going to wind up potentially with orthoclase alteration, and that's challenging to pick as well. People tend to go on colour, which is not great. In these two examples here, I'm showing you orthoclase as little pink veinlets, so it's a bit more distinctive. But this example of a quartz diorite porphyry from Boyongan in the Philippines, this is the front of the drill core, this is the back side, and we've etched it with hydrofluoric acid and stained it just to show you that all that yellow is orthoclase, and it tends to get underlogged as to its intensity, but that's the sort of stuff we expect to see in the guts of a porphyry. On the sides of the porphyry, as I've already mentioned, the alteration varies depending on protolith. So if you're in volcanic rocks, you get green rocks. You'll get epidote, chlorite. Close to the porphyry, you'll get actinolite. Same sort of thing will occur if you're in batholiths. But if you're in carbonate rocks, you're going to see skarn and marble, and the distal halo to your porphyry will be little calcite veinlets and maybe manganese-coated fractures. So they're much harder to pick up far away in carbonate rocks. If you're in carbonaceous mudstones, you get a huge pyrite halo. At Pebble in Alaska, the pyrite keeps going 10 kilometres away from the deposit. Normally it goes 1 to 1.5 k's out from a big porphyry system. And if you're in quartz sandstones, the alteration mineral is quartz. You wind up with a quartz cemented sandstone. People map it as quartzite, and all you can do is map quartz vein intensity and the crystallinity of the sandstone. So it goes from a granular quartz sandstone to a more and more crystalline rock. People mistake it for a metamorphic rock, but it's actually the alteration halo to the porphyry when you're in quartz sandstone environments. Now, when you go up from the porphyry, we enter this complex domain where phyllic and intermediate argillic alteration may overprint the porphyry. The degree of telescoping, which is the amount of superposition of shallow features into the deep features that occurs as the landscape evolves over the life of a porphyry, the landscape generally degrades and erodes. So we get this superposition of white mica and clay alteration over our porphyry. And every deposit's different as to the degree this occurs in. If you're putting white mica over biotite alteration, you tend to get phengite, so people will be referring to this as green sericite or grey sericite, depending on its composition. And if you've got more acid fluids, you get more muscovite, before you transition up into genuine high temperature clays. And there's quite a debate going on in the literature at the moment, and it's going to keep going for a while, about when does the copper come into these systems and the gold. Clearly in some porphyries there's a lot of copper and gold added during potassic alteration. These are examples from Boyongan where the copper is clearly associated with orthoclase alteration. And there are porphyries where the copper is at least in part associated with white mica alteration. So this is Rio Blanco in Chile. These beautiful tourmaline chalcopyrite, pyrite cemented breccias are associated with intense muscovite and phengite alteration. So the grade can come in at different times. And the truth is, the best porphyries, all of their paragenetic stages are productive. So a place like Resolution, it has the full suite of alteration. Every paragenetic stage added more grade. So if you want a really high-grade porphyry, that's one of the keys to success. Really difficult to predict where that's going to occur. Now, if we go above our porphyry, we move into this thing that we refer to as a lithocap. And this is the Cathedral Peak lithocap, sitting 3 kilometres to the west and 1 kilometre above the Cerro Casale porphyry in Chile. These are real challenges for explorers because they're enormous. They can be more than 10 kilometres long. They can be more than 1 kilometre thick. They can overlie porphyry deposits, and they can host high sulfidation epithermal gold. The lithocap in the bottom photo here is Tantuatay in Peru. It contains at least 5 epithermal gold ore zones, oxide high sulfidation ore zones. There's carbonate hosted mineralisation to the side of it and below, and there's a porphyry prospect there as well. These are where the gases coming out of the intrusive complex migrate up towards the surface. The gas is the main volume of fluid released from the magma. It carries sulfur dioxide, it carries hydrochloric acid, and so as it migrates from the high temperature part to a lower temperature part of the system, it undergoes changes that makes waters more and more acidic. And so we get our most acidic hydrothermal fluids on the planet forming in this environment above your porphyry. pHs can get down below 0, and that means we wind up with silicic and advanced argillic alteration. So a lithocap is basically where fluids are coming up an upflow zone, and eventually they will find a lateral outflow zone. If the gases condense into groundwater, that liquid does not want to flow up to the top of a mountain. It will flow laterally in some sort of permeable aquifer for kilometres away. And that means porphyry deposits can be offset from where you are seeing your lithocap. And let's take a look at Lepanto in the Philippines as an example of that. Lepanto and far southeast are a high sulfidation and porphyry deposit that are genetically linked. They formed 1.5 million years ago. The far southeast porphyry is shown here on the right. The Lepanto energite ore body is shown here in grey. That energite ore body formed at the intersection of the Lepanto fault and an unconformity surface between basement and a pyroclastic cover. And the Mankayan lithocap hosts that ore body. So the quartz alunite alteration extends much further than the ore zone, and you can see it actually crops out as a cliff several kilometres away from the porphyry. And above the lithocap are weakly altered rocks. People don't generally get this, that the lithocap isn't the surface. It may have a surface feature where hot springs are discharging, but that surface discharge can be kilometres away from where the fluids come from. And what that means in exploration, well, if we imagine this in older times, okay, this is a bit of a zoom in on Lepanto far southeast. Lepanto is hosted in quartz and quartz alunite altered rocks. They are hard. Far southeast is clay altered above it. So if we weather this over time, you will get topographic inversion. And so if you start drilling a lithocap where you've got this silicic and advanced argillic alteration cropping out, you might find your high sulfidation ore, but as Greg often talks about, you need to get on the shoulder to look for the porphyry itself. You can see actually the porphyry sitting in the low part of the topography beside the lithocap. So people waste a lot of money drilling through ancient lithocaps looking for the porphyry beneath it. Be aware asymmetry is to be expected. There's an unusual variation on high sulfidation themes that shows up in Peru, and I believe shows up in other parts of the world that hasn't been found here yet. That's carbonate-hosted high sulfidation mineralisation. Our standard high sulfidation gold deposits, this is Lazanja in Peru. You can see lots of gold in vuggy quartz there. Down here, this is former limestone replaced by energite and pyrite and quartz. That's sitting in this environment here. So if you've got a carbonate host rock and you form a high sulfidation deposit in it, amazing things happen. So if we look at Colquijirca in Peru, we have this large dacite dome complex in red, intruding a sequence of limestones in different blues and then some red beds. And we form this 8 kilometre long zoned mineral system. It's just amazing. At its core, it has vuggy quartz with gold, and here you can see coverlite filling the vugs. But then we get these ore bodies continuing off into the carbonate rocks, both north and south, and they're zoned from copper and gold to lead and zinc. And we don't think about lead zinc ores in high sulfidation deposits normally. Here's just a little cross-section showing you how those ore bodies, shown here in black, sort of go out into the carbonate rocks. So they're quite erratic in their distribution, but in plan view, when you look at the metal zoning, and this is just the northern part of the district, and you can see the 500 metre scale, going from the volcanic hosted sector at Marca Punta, we get copper and gold. The copper is extending 3 kilometres north through the carbonates, but we're getting 10% zinc and 3% lead grades up there in the carbonate rocks. So carbonate rocks neutralise acid. If you put a high sulfidation deposit in the carbonate rocks, you will get a polymetallic system. And you can see here the silver 3 ounces per tonne and higher, also crazy bismuth grades. You just basically trap every metal if you've got the right reactive rock. Now, the other family of epithermal deposits, which get called intermediate and low sulfidation epithermal, it's a terrible nomenclature, and Greg is going to happily explain why carbonate-based metal and quartz pyrite veins and the like are better, more practical terms. These are probably the most challenging deposits to find in a porphyry mineral district. Ultimately, they're controlled by structure, so you need a good structural geologist, also by rheology contrasts, and also by chemical gradients in the local protoliths. So there's a lot of variables that come together to influence where they might form. And because they form in the shallow part of the Earth's crust, many of them form a kilometre or shallow, there's far more opportunities for fluids to flow in different ways. So we get veins, we get stockwork arrays, we get breccias, we get disseminations. They're highly variable in their form. So basically, if you want to find these deposits, you need to map out your structural architecture really well in your district. But when you do find them, you want to think about the potential of the other deposit styles that might be nearby. And they can be truly spectacular in their mineralisation. They will be gold, silver mineralised. Some of them may have high base metal contents depending on the salinity of the fluid, so you may get a bit of sphalerite and galena. They're not usually copper mineralised very strongly. And the classic model, this is the old Buchanan boiling model, showing you an extensional vein array with a hanging wall split. That type of structural architecture does occur. Some of these deposits look like that, but many do not. So expect a high degree of variability in these systems. They're always a pleasure to find. Just take a while to really unravel. Now I wanted to also go a little bit into skarns and carbonate replacement deposits, because when you have reactive rocks around a hydrous intrusive complex, you have the potential to produce a skarn deposit. And in some districts, these will be the principal resource. Sometimes skarns suck all the juice and all the metals out of a porphyry, and you get a reasonably barren porphyry next to a well-mineralised skarns. In other places, you'll get really good grades in both the skarn and the porphyry. So they vary from place to place. A little bit of skarn 101. If you put an intrusion into a mixed package of carbonate and clastic rocks, and you've got a thermal aureole around that intrusion, so our deeper intrusions generate large thermal aureoles, you can produce what we call a reaction skarn. Okay, so here we've got a sequence of limestones and shales interbedded. They get metamorphosed to marble and hornfells, so we're getting a calcitic marble and a biotite hornfells, and a little bit of chemical mass transfer can occur across the bedding planes. And we wind up with these beautiful and spectacular banded skarns that you see here. This is from King Island, so this is down the Dolphin scheelite deposit. Biotite hornfels layers, marble layers, with interbands of garnet and pyroxene, brown garnets and green pyroxenes here. These type of skarns, these reaction skarns, are usually not mineralised. They may be the biggest skarn footprint around an intrusive complex, particularly at depth. So they're a sign that you're getting in the right place, but they're not the key thing for mineralisation. What we want to find is infiltration skarns. Okay, so when a hydrous magma releases its fluid into the surrounding rock mass, we get a lot of metasomatism. Chemical mass transfer is taking place, and we alter the host rocks and we alter the intrusion itself. And that's why we wind up with these terms endoskarn and exoskarn. So an endoskarn forms within the intrusion. You can see here garnet veins with green pyroxene halos overprinting a feldspar porphyry. And the exoskarn forms in the surrounding reactive rocks. And we tend to think of carbonates being the reactive rocks, but it can also be ultramafic rocks, it can be mafic volcanics, it can be calcareous volcanoclastics. There's lots of opportunity to form skarn. If the host rocks are more reduced, you tend to get pyroxene and magnetite, as in this banded magnetite pyroxene skarn here. And in more oxidised rocks, you get garnet skarn. So dirty big garnet just sitting here in this drill core from Las Bambas. And then after this prograde phase, when we form our skarn minerals, so pyroxene, garnet, wollastonite, they're the minerals we use to define skarn. But later hydrothermal fluid then comes along and produces a retrograde assemblage. We call it retrograde skarn. It's lower temperature. It's not genuine skarn mineralogy. And if you compare these cartoons, you see the retrograde phase has actually the widest extent. So we go from the genuine skarn environment into the surrounding wall rocks. And we may wind up with carbonate replacement mineralisation, such as the pyrrhotite, cassiterite ores down at Renison in these altered dolomites. We can wind up with widespread epidote metasomatism. So a lot of the times the mineralisation's actually coming in during this retrograde phase. Now, just to show you a place in Peru, this is Las Bambas, a giant cluster of copper skarn deposits. Just to the south is the Hikira porphyry deposits, which are hosted in quartz sandstones. But just to highlight here this mineral system, there are over 40 intrusions on this map that you're looking at. You can see the 5 kilometre scale bar. And they were in place between about 41 and 31 million years. The intrusions become more fertile and ultimately produce mineralisation over time. You see that the early intrusions are big plutons, and then we go into stocks and dike swarms. The red ones are the ones that are syn mineralisation timing. So basically this district is uplifting and eroding, and so we're seeing smaller intrusions because they're in place closer to the surface later. 3 giant skarn deposits, Ferrobamba, 1.3 billion tonnes, Chalcobamba and Sulfobamba, similar sort of, several hundred tonnes. And they're associated just with single discrete intrusive phases. So not all of these intrusions have produced a skarn deposit. Ferrobamba, the best of them. I just want to show you a little bit at Chalcobamba, because when you're in a porphyry district, you commonly get iron, copper, gold skarns. Now in this case, this is an iron copper skarn. This is the cross-section at Chalcobamba. You can see we've got these big intrusions at depth and several dikes. And then we've got this hill up above 4,500 metres with garnet pyroxene skarn in green, magnetite skarn in black, and the 2% copper ore shell sitting in that skarn that you see here. And those rocks, just to show you what skarn alteration can do, this is your retrograde skarn. That's all epidote sitting below magnetite here. So these are all late phases. The magnetite's coming in late. Here's a magnetite, massive magnetite with chalcopyrite all through it. This is their ore. Garnet going into the marble halo cut by epidote garnet veins. And so this sort of stuff looks like what you see at Big Cadia, this massive magnetite that has replaced garnet, and then you get these calcite, chlorite, epidote-filled pockets that wind up with the copper. So the copper's coming in late in these rocks. So that's sort of what we expect to see around porphyry systems. Skarns are much more diverse, so you can see them in granite-related systems. So we get tin skarns, tungsten skarns and the like, but they're absolutely a viable target. So with all of that, what's our potential in the Tasmanides? Well, we've already found all this stuff in the Tasmanides. Just here in the Macquarie Arc, we can go out to North Parks and see porphyry copper mineralisation, and we can see the remnants of a lithocap at Nash's Hill. We've got high sulphidation epithermal deposits at Peak Hill at Gidgeonbung. We've got intermediate sulphidation deposits such as over at Endeavour 44 or at Cowell, and we've got skarns at Trundle Park, at Cadia, at a bunch of places. So all of these elements of the porphyry mineral system are here to be discovered. The key thing is we should always remember every place has its own quirks, its own variations on a theme, so don't always expect that what you see in one province is what you're going to find in another. You've got to be adaptable and flexible. So with that, I'll wrap up. Basically, hopefully it gives you comfort that what we have here in the Macquarie Arc is normal magmatic related hydrothermal systems. It's just that they are old, so they've been disrupted, so their preservation is a challenge and their segmentation is a challenge. So we have to work through those additional challenges of having ore deposits that have been deformed, buried, maybe cooked up a little bit. But if you can find an oxidised hydrous magma, you're in the right address for a porphyry. And once you've got that, if you've got shallow environment, you may get your high sulphidation, your structural controls and your intermediate sulphidation, and your reactive rocks give you your carbonate replacement and skarn deposits. So with that, I'll wrap up. Thanks for listening.